Hi everyone, welcome to Advent of Code Day 21. This video I'll be showing off I'll be live coding my solution in Python so you can see how I approach the problem and work my way through it. Looking at the leaderboard, this took people a really long time, so we'll see how far I can get, but hoping to put in at least a couple hours and really try and work through this. All right, let's get into it. Day 21, step counter. You manage to catch the airship right as it's dropping someone else off on their all-expenses trip to Desert Island. It even helpfully drops you off near the gardener um, and his massive farm. You got the sand flowing again. Great work. Now we just need to wait until we have enough sand to filter the water for Snow Island, and we'll have snow again in no time. While you wait, one of the elves that works with the gardener heard how good you are at solving problems and would like your help. He needs to get his steps in for the day, so he'd like to know which garden plots he can reach with exactly his remaining 64 steps. He gives you an up-to-date map, your puzzle input of his starting position, S, garden plots, and rocks. For example, the elf starts at starting position S, which also counts as a garden plot. Then he can take one step north, south, east, or west, but only onto tiles that are garden plots. This would allow him to reach any of those tiles marked O. Then he takes a second step. The second step would allow him to reach any garden plot. Okay, that is exactly one step of away from anywhere he could reach with the first step. So notably, he can't reach these spots, which he was at before. Um, cool. After two steps, he could be at any of the tiles marked O above, including the starting position, either by going north then south or going by west then east. Okay, it keeps going, 6 steps. Yeah, cool. So I don't think this should be too hard. Let's, at least for part one, let's paste in our input. And, okay, so here's our example. Maybe let's open that in a second. Split. Cool. Set up our watch script. And let's get into it. So, I think, first let's find the starting position. For y line and enumerate lines, for x char and enumerate line. If char is equal to s, start x start is equal to xy. Cool. Then assert start 0 is greater than 0 and start 1 is greater than or equal to 0. Cool. So this should get our start position. And I think what we can do is simply run depth first search from the start, and or breadth first search, either works. And every time we get to a point, excuse me, we can count the number of steps it took to get there. So maybe we run BFS. Yeah, let's run BFS. And then we count the number of steps to get there, and we can only end if the steps to get there is divisible by 2. So for example, like if our we could never get to this square because we can only move in cardinal directions. Um, so we start here, this takes 1 step, then we can only essentially shuffle back and forth 63 remaining times, and we'll never return to this square. Um, yeah, so let's just run BFS for 4 steps. Let's define a couple things. Point, define this type, is equal to tuple int. Um, then directions is equal to this list of points. And we have 1, 0, negative 1, 0. Just getting the cardinal directions. 1, 0, negative 1. This is just point. Now we can run BFS for range, I guess for step in range. We'll start with just 1, I guess. Yeah, and then to visit will be a list of points, and initially just equal to the start. And then we'll create a new to visit, which will update, and then to visit equal to new to visit. Cool. For point into visit, let's also keep a set scene. For point into visit, we can first check if it's in bounds. So m will be the number of, sorry, yeah, m will be the number of rows, and n will be the number of columns. Cool. If x is less than 0, or x is greater than equal to n, continue. If y is less than 0, y is greater than equal to n, continue. Otherwise, for dx, dy in directions, also if excuse me, if lines x, y, I guess we can just destruct this here. Lines x, y is equal to a rock, continue, dx, dy in directions, new to visit, append, x plus dx, y plus dy, and then here we can do scene.add xy, and we can also do if xy in scene, continue. And we also need to do, okay, instead of scene, we should be um, is it n steps, which will be a dict of key is a point, value is an integer. Change this to n steps, and then n steps xy equal to step plus 1. Yeah, okay. Cool. Let's then print out steps. Oops. This could go here. Delete these extra lines. Okay, this I guess can be like this. It's 4, 5, 5, 4. Cool. Then I guess one if and step in one if step mod 2 is equal to 0 for step in and steps dot values. Oh, this is cool. And this could just be a sum. And let's change this to 16. We get 42. That's too high. Oh, sorry, 6. We get 16. And that's correct. Okay, cool. Let's run this on the full input. 43, that seems too low, probably because this needs to be 64. That's correct. Nice. All right, well, part 1 was pretty quick, but part 2 is the slow part. Let's now look at that. Val seems confused by your answer until he realizes his mistake. He's reading from a list of his favorite numbers that are both perfect squares and perfect cubes, not his step counter. The actual number of steps he needs to get to today is exactly this big number. He also points out that the garden plots and rocks are set up so that the map repeats infinitely in every direction. Okay, this is interesting. Oh, this seems like a good problem. So if you were to look at one additional map width or map height out from the edge of the example map above, you'd find that it keeps repeating. This is just a tiny um okay, the map keeps repeating, it's tiled. Um cool. So every other start is marked to the normal garden plot. Okay. So this is obviously makes things much more complicated. Because now we can leave the map. Hmm. Is this brute forceable? Probably not. Um, Especially because we can get this far out. I don't think it's brute forceable. Well, I don't think the solution we want to initially consider. Okay. Yeah, so I think we're gonna somehow need to like analytically compute the solution. So I'm wondering if like we can count the number of steps it takes to get to each one of these like boundary points, maybe. Yeah, this is really hard because obviously we still care about like um the thing where like all steps the distance needs to be divisible by 2. Excuse me. So for this grid itself, if we have 64 or like uh, a massive number, oops, let's run it just on the example. This should be the same. 42, whether it's 64 or something giant, because we totally fill it out. But obviously for the infinite case, that's not true. Um, and so what's interesting is like sort of on the boundary, we'll like sort of wander off from the starting point in every direction. And then on the boundary, on like the limit of the square we can hit. Um, so say it's like 10, obviously, well, maybe not, but say it's like 100. We'll fill up this square. We'll probably fill up all these squares, but there'll be some square where we can make it into the map, the copy of the original map, but we won't entirely fill it out. And so that's interesting for sure. Um, Something maybe we also have to think about is it's like 1, 2, 3, 4, 5, 6, 7. Um, 8, 9, 10, 11, 12, 13, 14, 15. So we actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, so we actually reach the start on this next grid in an odd number of steps. Excuse me. So the squares we fill up on this neighboring grid will be different than the ones we fill up on this one. Um, yeah, this will require a bit of thought to figure out how we want to do this. Um, so I'm not totally ready to code up, but let's just, um, I guess, get some of the things ready. So I know we'll still want to find the starting position, and then we'll still want to run BFS. Um, this time, I think that, or I'm assuming we're still going to want to run BFS. I think that this time, excuse me, we will, instead of for 64 steps, just run it till it's completed. So here, this will be wall to visit. Um, Step 0, step plus equals 1. And then let's just print out what this looks like for y line and line enumerate lines for x char and enumerate line. If char is equal to block, we can print just a block else, print step is equal to and steps x. These should all be in the dictionary. If step 2 is equal to 0, 1, 0, print 0. Else 1. And then at the end of each row, here, else if x, y in n steps, else just this is weird. We should. Why are there some places that we never reach? That's tricky. And this is our start? Like, why do we never reach there? Okay, it was just a printing thing. Cool. It's a little busy, so maybe okay, so those are the places we can reach. Maybe let's put the start on there too. This is really not essential, but if lines y x. So I guess we have a square input since this works. Lines yx from the start. We'll print out well, now we've printed and don't actually haven't worked towards a solution, but yeah. Okay. Okay, I'm just gonna take a couple minute break. I'll come back and continue. Um, Not like fully stumped, but I think a break would help. All right. All right, I ate some breakfast, but now I'm ready to get back into it, and I think I have an idea about how we can continue. So let me first just write some quick code up and then explain it more in more detail. All right, lines. Um, Count is equal to sum of the walls in the row. For char in row if char is equal to wall, if y is equal to 0 or y is equal to m minus 1, assert wall count 0, else assert wall count is greater than 0. Okay, that looks like it works. Now to do this for the columns. For x in range n, call is equal to row x for row in, line x for line in lines. Change this to call, change this to x equals 0 or x is equal to n minus 1. Okay, so what we're doing here is checking that each row, each of the first and last rows is empty, and each of the first and last columns is empty, but none of the other rows and columns are empty. Why this matters, let me go into in a minute, but let's just make sure this is true for the full input. Okay, it appears it's not true, which is going to throw a bit of a wrench in this. Okay, let me look at the input a little more. Okay, that's interesting. Okay, it appears that if we go straight up or straight down, then there's nothing. Um, yeah, that's odd. I mean, it's helpful, but also it's strange that the full answer has that, but not. Um, but not the example. Because okay, let me just explain what I was thinking. Um, this is where it'd be nice to have some way to draw if I had like my iPad. Draw a line. I don't know what this shit is, but we'll go for it. Okay, so what I'm thinking is, okay, this is going to be not ideal, but um, okay, we can make it work. I think. So we have our just stay the same width. um, and the line should just be a constant width. Okay. Um, Maybe a little bit thicker than that. Okay, so we have our starting square that looks like this. We start in the middle. What I noticed about the example is that we're surrounded by single dots, or like each row and column of the starting input. The first row and first column and last row and last column is empty. It has no blockers. And so what that lets us do, um, but I guess what I also noticed is that this interior, so if we go one row in, it does have some boxes in each row and each column. So what we can think of is when we are tiling this out, so here's the second one, um, and then this middle one is like our true center or whatever. How do I like, uh, fighting this just a little bit, but let's make it a little smaller. Delete these, copy this again. Okay, so this is our true center. We're tiling them out like this, right? So there's one empty column between here, and similarly like above and whatever. But what we care about for now is, so we'll keep track of this as our true center. Let's do this one. And then this one will just be there for me to copy and paste. And yeah, so we basically have like a bunch dot 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 dot. This is like, say this is times 1000 or 100 because these are painful to draw. So if we want to go from this original start to a tile on this grid, the fastest way to do that is going to be to get to this corner and then just run along this open line, and then we can go in. So the fastest line is going to be like this. The fastest way to get to this square. Why that's notable, excuse me, why that's notable is that is that or why that's true is that because we're taking like the Manhattan, or the distance where we step like this, um, since there's no way to go straight through like this without having to do something like this, even though to get to from like here to here, say, we have to go first down and then back up in the limit. So this would not be true. For example, it'd be faster to go like this than to this corner and then up. But in the limit, if there are a bunch in between, then it's going to be faster to go first to this corner along this open line and then up. Um, yeah, cool. And so that's what I noticed about the input. And that what that lets us do is sort of simplify a lot. I'm interested to see how other people approach this. So this is not going to be a fully general solution. But then what I noticed now, what we see about the true input is that it's different, which is a little annoying because we have this, instead of looking like this, we have something where it's the start and then these corridors from the start. This is like a star in the middle, it's a square, are open. And so now the fastest way to get from the start to to here, if this is in line, is just straight like this. Um, yeah, and what this just makes it a little bit annoying, but it's fine because the example is not like that. Uh, excuse me. Since the example is not like that, like for example, we can't just go straight down. Um, we can, we're gonna have to have slightly different code for doing the example versus because example is nice because you can check your work. I think what we're gonna do, because it's so key to be able to check our work, is that we're just gonna do it on the example for now, and then it should only be a small change to address this case in the full input. To do full setup for full input. Okay. Um, yeah. So, whoops, and then just so we can look at the example again. Cool. So I think what I want to do first is bring this BFS out into its own function. Def run, or let's go call it BFS. And then I'll take lines and whoops, and a start. It will return that distance map. So a dictionary of point to distance. Um, okay, so I think this should just work. I guess we need to grab NNM. Now this should work. I guess while we're at it, we can bring this up into part one too. Excuse me, no, this is wrong. We can bring this back down because this is just going to be used in part one, part two, because we're running for an infinite number of steps. Okay, so we have our assumptions about the input validated. EFS start lines start. Now we can print out our nice picture. Okay. And then going back to our drawing, we can assume that like for this one, I mean, we're counting a massive number of steps. So this is not going to be a fully general solution if I didn't mention that before. Like it'll probably not work for these lower numbers, but will work for the higher numbers. We'll fill in this totally. So we want to find yeah, let's write a function that takes in the position of the final grid. So say we have say let's think how we want to do this. Okay, say we input a grid position where this is 0, 0, this is 1, 0, and this is whatever 1, 0, 1, 0. So the function will take in the grid position and then return in the limit the closest point we get to. Yeah. Yeah. Um, we'll return the closest point we get to on it and how many steps that takes. So we're thinking about exactly how this is going to look, but we can def get map entry. Maybe we pass in a number of steps. Hmm. So I think this is the idea. Then how we actually want to solve this is I think that we can iterate over each row. So starting at this middle row, we'll go from, we essentially need to find, so say that this block we can fully fill, but this block we cannot fully fill. So this is like half. And then this block is none. So essentially, as we're scanning out, we know that all these are full. So like this, we know these are all fully filled. Then this one's going to be half filled. So we're actually going to have to compute how many we can step to. And this is going to be not filled. Um, so I think that in order to find this half filled, we can just use binary search. So we'll go back to this thing and yeah, get map entry. So it'll return the closest point that we enter. Um, um, returns the number of steps to access each of the four corners of map. Um, so the signature will be map. Are these maps? What the fuck are these? Yeah, map X. I guess we can do map, and that'll be a point. Excuse me, map will be a point, and then yeah, and then it will return tuple of dict mapping point to end step to int. um, yeah, for the four corners of the map, because those are the places we're going to hit first. Um, so first, get the distance to the corners of the original map. So for example, copy these guys. Um, so and steps or here, let's call it just this steps or origin is equal to what I call this function, BFS lines start. Um, and then so I think that what we can do is compute the distance from each corner of this to each corner of this, and then just take the minimum. Um, yeah. So let's get here. Let's print out, let's call get map entry lines start 100, 100. What is this one? 100, 0. I guess 101, 0. So there's 100 in between. Yeah. Um, cool. So let's, I guess, get the origin corners is equal to a list of zeros is a list of points. And then we'll also get the map corners. So the origin corners will be, I guess 0, 0 is here. True 0, 0 is here. 0, 0, 0, m, whose number of rows corresponds to y. Let's just call this rows and columns. Rows, calls. I know it's kind of weird just doing this everywhere, or it just waste time, but I like to keep it clean. All right. Rows -1, calls -1, 0, rows -1, calls -1. I guess this is 2. Oops. And the map corners is going to be equal to for xy in origin corners. It's going to be a tuple of x plus the map offset is going to be map 0 calls times map 0 y plus calls rows times map 1. How long does this get? Too long? Yeah, let's print map corners and origin corners. So we have 10 by 10. So it's gonna be, yeah. Maybe to start, we can put our map at 1, 0 or 100. Is this right? No, it doesn't seem right. Like here we have, so yeah, the y is 0, 10, 0, 10. Okay, because rows and columns was 11. So this is right. And then we want to find the distance between for xy in map corners. So we can call this mx and my. And we're going to have another loop where it's ox, oy in origin corners. Corner dists is going to be a list. And then corner dist.append absolute value of mx minus ox plus abs of y minus oy. Yeah. And then map dists is equal to an empty dictionary, and then map dist of this corner, mx and y. Let's define how this is. This is a dictionary from a point to an int. Is equal to sorry, this is equal to fucking, I don't know. um, and then we need to add steps origin. This thing, let's copy and paste it here. Also, since I think it's going to be a factor later, let's change BFS up a little bit. To visit, to visit is going to be a list of points. Yeah. Map dist is equal to min corner dist. So this needs to also include the distance to the corner, steps, origin, OX, OY. And I guess we can print out the bug. Okay, so let's compute this by hand. So the two corners we care about are these two. So to get there, for example, we would do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then I guess to get to the closest corner, which is going to have an x coordinate, of 11, 10, a y coordinate of 10. Could add 14. Yep. And then sorry, so to get to this is 14 and top is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10. This is 0, 0. And then this is 1100, 0. So to get from there to there is going to be And this coordinate is a 1110. Why is that 1110? I know this is slow, but it's really crucial to not have any bugs here. So I already know that we're going to have to add 1 at the end of this because we need to step into the new block. So to get from here to here should just be it's from the origin, so it should be 1100 plus 14 plus 1. This is 1110, 10. So that's 1115. That's correct. Then to get to here, it should be 1100 minus 10 plus 15 is 1105. Yeah, so this looks right. This looks right. I guess we can't know if it's 100% right until, well, we won't know. Hopefully there are no bugs in there. Surely there aren't. Okay. And now I guess we, for each row, perform binary search to the left and right. Cool. Okay, let's also get the steps to fill from each starting point. This I guess should be called keep map corners. Map corner steps, maybe. I don't know. That seems to make a little more sense. But the steps to fill hit these. So low equals 0 for row. What is that? Row x equals map x equals 0. All is equal to 0. And then binary search. We want to do I will be total steps. For now, let's just set it to 1,000. Is that in our? while higher than low. Guess we don't need to keep track of call, so that's determined by this. Mid equal to high over low. And now we want to check the steps to reach mid. This might be too slow, but we'll try it. I'm realizing there are going to be a lot of rows to do this for. A lot. Maybe some memoization and splitting up into different functions. Yeah, whatever. Let's just try and complete the example, which will be more than hard enough, I'm sure. This is a big number, 26 million. Not, it's big. It's definitely big. Okay, sorry. So it's equal to map corner steps. Line start map row 0 column mid. And then I need to change up how we do our BFS. To visit, let's keep track of the steps in to visit. So to visit will be a list of tuples of points and steps. Okay, for x, y, steps, step, and to visit. Comma, step plus 1, and here can get rid of that. Or tuple starts 0. Sorry, this is I minus low over 2. Okay, this never ends, obviously. we don't want to do that. And then map steps is equal to print list corner steps dot items. Okay, so map steps equal to PFS lines list corner steps dot items, and then print max map steps dot values print max steps map steps empty. What? And then I guess PFS also needs a map argument. It's getting a little complicated. Let's put it here. Is equal to x origin is equal to x minus map 0 n times map 0. Y origin is equal to y times n minus map 1. N is the number of columns. Here is going to be x origin. And address these issues. Steps origins go like this. It's definitely inefficient. So this is the furthest point on the new map. It seems a little bit fine, whatever. So you do have to loop your way into here. Oh, is that right? Because you gotta get to here and then around. Okay. Whatever, I can believe it. Yeah, I know. Yeah, if max map step values is greater than mid. Do something else. Do something. Here, let's print low, mid, high. Greater than total steps. Comment that shit. Then high equals mid. No. Low is equal to mid. False. High is equal to mid. So since we're too high, then we're greater than total steps. We need to decrease arm range 10 on this shit. Cool. So eventually, low, mid, high. High is equal to mid minus 1. So mid's going to be 87. Or less. I feel like this shouldn't be necessary. 83, 83. I think I'm struggling with this fucking indices for binary search. So you don't get is when this is 0, low is equal to 87, high is equal to 88, or too low. So then low should increase by 1. 99. Okay, so I guess mm, print mid. Mid is bound. So mid is now the call index of the first partially filled. Um, it's also print get all of the partially filled maps. All true. Column in equal mid. All true. Column next mid. This thing is mad. Maybe paste this in first time. Check if partially filled. So this is with the max. Now we care about the min. So corner steps. Min. Print this. If the min is less than greater than total steps break. Otherwise, call max was equals 1. Cool. So we now know that 77 and 78 are partially filled. Wowzers, this is a complicated problem. Oh. Whoops. So I guess we want to create this list of partially filled. Um, Total steps. Partially filled by extend mid plus I for I in range partial buffer. Okay. And then let's run binary search to the left. I is equal to 0, rho is equal to negative total steps, while that is greater than low, for range 15, do all this shit. Low is equal to mid plus 1 here, right? This could be the last fully filled row. It is now the call index of the last fully filled map. Partially filled, dot extend. Mid -1 -I for I in range. Partial buffer. I think that is fine. Now we can do a call get the count of partially filled. A call in partial filled. App is equal to row call. No, call row. The row, the X should be mid row. Yeah, this needs to be flipped around mid row. Same here. Mid row, mid row, but everything should still work fine. App is equal to call row. App steps is equal to BFS. Corner steps. Call row. the map steps, BFS lines, call row list, corner steps dot items. Then row steps equals 0 to get steps for fully filled maps. Then we're going to count row steps plus equals 1 for maps, steps in map steps dot values if steps is less than or equal to total steps. I'm trying to decrease the size of the buffer by 1 mouse. Let's keep that for now. Get the steps for count is if row step 0 break print row steps, and then this thing is all going to get wrapped in for all true. Is equal to 0. Do need to go up and down, and then this we can comment out. Steps even is equal to mod 2 equals 0. Okay, so total steps is equal to 0. Total steps plus equals row steps. And print total steps. It's gonna be way too slow. Oh no. Because our final total steps gotta be this shit. VP, which is a lot bigger, and our code is still taking a long time. This needs to run instant, faster than instant. Okay, so let's make sure we get the right solution and then optimize. Is this, oh man, I don't know if this can be optimized enough. There's a lot of stuff that can be optimized though, so no need to fret. Um, um, how do we get the fucking corner steps? Print map corner steps lines start 0 0. Oh my god. So it's all odd. Which means it'll take an even number of steps to get to the next map. Okay, let's just do a little insert all s odd 2 equals 1 for s in origin corners. Where is this defined? It's not defined. S origin corners on values. Nice. And also delete this bullshit. Um, so then origin total is equal to origin total is equal to map step, sorry, origin steps is equal to BFS lines start 0. Origin total equals sum of 1 if or if s in origin steps dot values if s equal to total steps mod 2, get rid of this, close this shit, print origin total. That's not right. Print list origin steps values. If s mod 2 or 2, that's right. Now we can delete all this shit. And then for so then low is equal full low is equal to min partial filled plus partial buffer. Ooh, I think. Print full low. Full high is equal to max filled minus partial buffer. Allow full high. If full low is less than full high, then row steps plus equals origin steps times high minus 4 low plus 1 times origin steps. Origin total. Here, for example, we have no partially formed. Here we got a couple. Okay. I actually think this should work. 705381. Oh, please, maybe. Ah! No. God damn it. Oh. No. Okay, I wonder if we no, we're basically getting an answer that's too big. 703. I need a sec. Row. Okay, we're counting too many of these. The question is why? Um, on the column index of the last fully filled. Yeah. Oops. If something's strange going on in this and if low is equal to mid, and if greater than the total steps. I'm actually fucking stupid. I just can't understand this simple. Um, be a moment where they're equal. It should be higher. Conics of low, high, mid. Okay, I'm gonna take another break. Just, yeah, start one. All right, welcome back. It's a few hours later. I did a little bit more work and then took a pretty long break. But have made significant progress. A lot more to be done, but have made significant progress. What we're looking at here is a visualization of the example with a size of 100. And so this is actually correct. It's 6536 is what it prints out, and that's correct. So there's a bunch of things we need to do now, including, so this is not, there are a couple things I had to do to get here, but yeah, there are some issues still. Mainly that this isn't, I just manually put in the size that we want. It's also calculating all of these interior points, which is, it's way too slow. Also, it's, sorry, also, it's just slow. So if we run it again, but time it, you see it took 0.44 seconds. And this is like literally 5 orders of magnitude smaller than the actual input. So yeah, we kind of have to go through and fix all of that. Um, Yeah, so a couple things. One to note is that I initially thought that all these interior points would be the same size. They're not. So that is one thing to fix. Um, yeah, let's do that. Um, this is failing. Okay, so this means that we're sort of doing like an every other type of deal. Um, yeah. So now, so we have this origin total is 42. Then we also want to get a offset steps. Here, let's just copy this. Offset steps, which is going to be, yeah, which is going to be for this map. Starting at plus calls, start one plus rows, print origin total and offset total. Whoops. 0. Print offset steps. Okay, since it's 1, here we do 1, 1. 42. So this is going to be like this. Um, hmm. Okay, actually, I guess we can use the offset. Use the origin steps, but here add 1. This should give us 39. Okay, so now we have that offset total. Now we need to fix this binary search. Yeah, I guess we can do a bit fewer rows. Maybe a few more. So we have some new lines on either side. Okay, cool. So now we need to fix this binary search bullshit. So we have a lot of these comments. Just because they're clogging stuff up, I'm gonna remove them for now. And here. let's we have this partial filled. I guess for each row, let's also print. See what this looks like. So it actually kind of looks like partial filled is working. 1, 2, 3, 4, 5, 6, 7. Yeah. Cool. So I guess we can do something like let's create a new map called partial size. Just make a mark to remove it. And then instead of this, here we gotta uncomment this. And then here, we do for call in partial filled. Delete all that stuff. We have a bunch of random comments. Why is this so long still? And then partial. Here, what did I call this thing? Partial size. To map print. Map print. Dot append. No. Row call equal to map total. And now do a little bit of for x, y in, no, x in range minus 12, 12, or y in range minus 12, 12. Y should actually go first here. And then if xy in print, print, well, f string action, we want to do the count map print xy 0 2d and equals this, else print, and then spaces, and then okay, something goofy's going on here. I guess we need extra space here. Okay, so we can see that it looks like, why are we adding so many here? That doesn't really make sense. Why is these lists so long? I wonder if I have this. Yeah, this seems more correct for sure. I do wonder though if we're missing any on like the inside of this. What if to do maybe missing some points that should be missing some points partially filled and should be in this list. But we can sort of check that by seeing if there's errors. So then we need to get the fully filled. Here. Print row full low, full high. Now we gotta determine for each one of these rows if it's like 42 to 42 or what. So I guess if width is equal to all high, all width is equal to full high minus full low if full greater than 0. Um, just do something temporary. So map print row 0 equal to full width. This is 3, that looks like right. 7 looks right. 8 looks right. 9 looks right. This should be 13, 14, 14, 14, and so on and so forth. Cool, that looks right. Um, um, if full, if low plus I guess it's if full with mod 2 equal to 0, then we have row steps plus equals row width over 2 times origin steps plus offset total. Full width. Otherwise, else if full low plus row mod 2 equals 0, row steps plus equals full width minus 1 over 2 times origin total plus offset total. Row steps plus equals. Here, I guess we can do else. Here, this is going to be origin total, else row steps offset total. We can remove this, comment this, see what we are working with. 6536. Print total steps 6536. Is that right? Nice. So now let's try and see if this scales to 500. We can get rid of the 6, this code. Let's just return total steps. We can delete this, delete this. This is correct. Now total steps is, let's just crank it to 1000. We know that this is minus 100 to 100. Uh-oh, that's kind of slow. 668, 697. Nice. Okay, I'm gonna take a little break again and be back in a little while to hopefully finish this off within about an hour more. Yeah. All right, we're back. I'm ready to optimize this. Um, yeah. Okay. So a couple things I want to do. First, let's get this thing scrolling. Sorry, not scrolling, but um, actually, instead of setting a row range, actually starting from the middle and then going out until we find a row of all zeros. Um, yeah, maybe let's make a new function. Um, def, call this maybe, um, row loop. I don't know exactly the arguments are, but it's going to return int. And then, okay, let's move total steps and partial buffer to global scope. And this is going to be while true, row equals row start, int, and then direction int. I'll just call this step size, step direction. Row is equal to row start while true. Comment out map print for now. If row steps was 0, break. Row plus equals. Guess we're call this row index. Row index. Row index. Same here. Row index. Index plus equals step direction. And what else do we need? Getting rid of map print. Total up is equal to, what do we call this? Row loop. Row start is let's start at 0, direction 1. total down, row loop, start at -1, go -1, and then return total up plus total down, and then return total steps. Oh, where did I just jump to? Needs to be row index. Cool. What else do we need? Let's move let's move origin start, which is a point. And this to origin start lines. Let's pass in the origin total and offset total too. And let's format. Nice. Now the only issue is that we need lines, and then here we need to start, origin total, offset total, similar here, start, origin total, offset total, and then let's move lines to a global scope. I guess this will then have to be moved to the bottom. And then, yeah, we can use the global lines. Whoops. Basically, in each function signature, you can remove lines. And then this should fit now. Cool. A bunch of places where I don't have any problems. Okay, this is one. There. Still mad about lines. Here too. Okay. Let's see what we're working with here. Okay, slow. Let's okay. I don't think we need this window anymore. That's working now. but it's become quite a big function. See how long 5,000 takes. And remember that we have to get a lot bigger and with a bigger input. So it seems to be scaling linearly, which is good at least, and that's, I think, expected. But there's a lot of optimization to be done. So that's 16733,044. Okay, cool. So the optimizations I see, we can improve our, since we expect our thing to be shaped kind of like this, like a big diamond, we can improve the bounds when we're starting from the middle. Inside of row loop, when we run the binary search, so if we get this index and then count in 2 and start our search there, I think that should be good. So what if we set here define some new variables? Prev right is a point, and that will be have initial values of low. It should just be a single thing. Next right point equal to 0 total steps, and then next left point equal to negative total steps 0. And then here we can unpack low highs equal to next right, low highs equal to next left. Make sure that this works. And maybe we can change this guy to 1000. Okay, so well, let's benchmark using the 1000. So we're starting at 1.8 seconds, and really we want to get that down to something like 0.1, or ideally lower. Now let's benchmark with the 5K. So we're starting at 10 seconds, and we want to get that down to 100.1. Okay. And then let's update next right equal to, so the right bounds
they should get smaller. So high is equal to mid. Um, high is equal to mid, low is equal to mid minus 2. I think that should work. Next left is equal to mid plus 2. Oops. So that got a slightly different answer. I wonder if this helps. Uh-oh. That's interesting. That gives us 729. 759. Um, Funny that that takes so long to convert. Why would that be the case? So we start out as mid and then we do the search from like there to there instead of there to there. It doesn't make a great deal of sense. Where mid minus 10, mid plus 10 would result in a loop when this doesn't. So this is the issue. It's not on the high, it's on the low, I think. If here we do max, something like this. and 7. Now we're creating all these weird parameters, but this will be what should we call it? Binary search offset 2, sure. So these bigger is safer, smaller is faster, bigger is safer, smaller is faster. I mean, ideally, I don't think you would create weird parameters like this, but hey. Um, Next left, do mid, max, mid, plus, binary search offset 0. What are you mad about? Oh, this should be min. Damn it. 668, 697. Okay, there we about doubled our speed. Let's benchmark it on the 5K. Nice, so that's a huge improvement. However, I think that we're going to want to use little functools cache on some of our functions. In particular, this one probably not. But map, I think BFS is going to be the main one. And then to visit, I think we're also going to want can we redefine what it is? Um, and then wherever we call this, it's gonna have to be like this. Here, and then here, 63. So this should be something more like n for n in v for v n to visit. To visit is initial to visit. What are we calling this? What's it mad about? And 100 steps origin. What's mad about this? Because it's gotta be like this. Now it's mad about line 230. Here we also check this. Okay. And remove this printing in VFS. How long did it take before? That definitely proved it. Not that much. I mean, we're now to 1/5 of the time. Getting a little worried that we're like, yeah, getting a little worried that we're not going to be able to optimize enough to make this actually work. Much bigger total steps. Because we also have to do some more stuff with the input, but yeah, let's go through these where we call this. So this is fine. here. We can do some optimization, I think. Although we're still calling it with the map. That's kind of an issue. Why are we calling it with the map? Just so we can map to the x origin. Let's remove the need to call with a map. I think that'll help us big time. And because we should hit the cache pretty frequently. Which means we'll need to change how this works. OX1, OX2, here, MX is equal to x plus calls times map 0, y is equal to y plus times map 1. Just OX1, OY1, and then no longer merging corners should give us the same solution. Nice. Let's also just move these to global scope. It's interesting that that is slower. Now remove all those. Part 1, let's just return -1, just so that our timing is accurate. And then this should be x1, y1, and then when we call BFS, in here, map corner steps, should now be able to be called like this. And then not 100% sure that's gonna work, but okay, that did indeed work and was great for our speed. Now we can eliminate this parameter. Eliminate this. Whoops. Always good to run it, make sure everything's still working. Okay. Go to the references again here. Do a little bit of that. Do a little bit of that. A little bit of that. Do a little bit of that. Okay, we are starting to go pretty quick here. Now let's have corner steps. Let's see. Whoops. Do a little GR. Do we really even need that? Okay. Maybe we can list that later, but for now we don't need it. Now map corner steps. Instead of returning a dictionary, should return what we plug in to BFS, which is a tuple of a tuple appointment. Tuple of a tuple. And then steps. I should also include a int, because this is going to be wrapped in another. This could be a list. This is getting complicated. Format action. Do a little down here action. Offset is equal to step offset is equal to min steps map dot values, and then corner list is equal to 4kv in steps map dot items, and we're going to be returning the corner list and the step offset. This is going to be a tuple of key and this is going to be the point corner steps, and then corner steps minus step offset. Cool. And then gotta go to the places where we use this shit. Corner steps, comma offset, step offset, corner step, tuple corners. Use plus step offset. And then we have to do that 2 more times. Just make sure that we're erroring not at that part. Yeah, here it's gonna be corner step offset. This is gonna be corners. And this could be plus step offset. And one final place. This could be corners. Could be corners step offset. S plus step offset. Is it even right anymore? Uh-oh. Well, redoing all that is probably gonna be a nightmare. Uh-oh. Uh-oh. It's probably not even fast enough. All this shit even improve the speed? No. Kind of like the syntax. Or cleaner. Oh, it's moving it back, huh? You don't like that? Maybe it did make it faster though. This is 0.127. Up here is 0.166. Okay. It did make it faster, but it's wrong. So you win some, you lose some. Calling this a fuck ton, but now we have it normalized, I guess. Um, I'm doing some sus shit here. I don't know exactly what that is. Hmm. So close. So close. Just don't know. Looks like we might just be able to brute force this guy, but no. What's that? 1 million? Probably not a fair test to be running this at the same time. Okay, well, instead of optimizing, we'll just again take the version that works. Being very pragmatic here. Alright. See, what about when you run it on the full input? Uh-oh, uh-oh. I don't think it's gonna be fast enough, guys. Um, yeah. Not looking good to say the least. How long is that? That's for 100,000. You have to multiply that by 200. Um, okay. I don't know. Definitely doable. Um, and then, those false. And then, I'll, just make this guy, um, verbose and row index mod 1000 equals 0 print row. I don't even know if it's the right answer though. That's kind of the issue here. Is that scaling sublinearly? Hugely sublinearly. That's kind of sick. Um, print time not perf counter um um we change this to in print array one if print array is greater than 0 and what the fuck? See, we finished up. Or, oh, well, that was. Oh, did it do it? Yeah, but there's still some other stuff we have to do. I think this is fine. I think the main thing we have to do is going to be in the corner. As we can pull start thing into global scope. We're pulling a lot of shit in global scope, but who cares, man? Because we need it in this. Maybe we just didn't have to pull it in scope, but here we are. It's funny that 1,000 versus 1,000. If this runs a lot slower, I'm gonna be confused. How much? 8.7. It's funny that pulling this stuff in voloscope seems to slow it down. But whatever. Take this down to 100,000. I guess it's that first binary search is slow. I wonder if this makes a difference. Sort by OBS. Python is just using one CPU. Is that the same answer? It's not. It looks like it does actually matter. Yeah. So 131 by 131. 77692. Should we go before at least? Because it's a square, but this shit should not be like this. Who cares? The square. Does this really just work nice like that? So here's a test. Try it again on the example. Because it should be the same. Input, example. I think this thing is what's right. Um, Hmm. I feel like this is wrong. Only slightly, but I think this is wrong. Like these 4 rows should not be leading us to get an incorrect answer. Where's that print every fucking bullshit? Turn off. See, that doesn't make it. Yeah, I don't know. I don't know why these are messing it up, to be honest. Truly don't. Um, what is going on? Oh, what's going on? What's going on? The enemies should not be increasing it as far as I know. Where do we use the origin corners other than right here? It's just right here. Uh, hey, wait, we might just be onto something. I think that this, oh, yeah, okay, it's because when we have both, then it's getting messed up because I think it can nav right through, but it can't. Um, cool, let's, get our print every shit set up again. Then let's, um, do that $1 million run just to set things up. Um, yeah, here we go. Whoops. Maybe let's print everyone is owned. But to be honest, this can probably be print one if not the most efficient beast, is it? No. Memory's looking okay. It's not increasing. Seems like some of those optimizations could have been good. But yeah, the memory is fine. It's gonna take about an hour to crunch this whole thing. Wow, that'd be sweet if it was correct, huh? Somehow I just not sure that it will be, but we'll see. Make sure I got this total steps typed in correctly. 21, 501, 365. Okay. Minute 44 total, got to about 7,000. So, yeah. Let's, let's do it. All right, well, this run's gonna take about an hour. So, I think gonna just pause the recording, come back, and yeah, I don't know. We'll see. I'm not super optimistic, as you can probably tell, but yeah, we'll see. In the meantime, I might look at some of the actual solutions too, because if this doesn't work, I just don't feel like debugging it, to be honest. But yeah, pause it now, see it when this is done. Well, this finally stopped, got a value, and guess what? It fucking worked. So that definitely feels really good. Um, didn't even take that long. Well, 30 minutes. Did take quite a while. But yeah, that was, this was a crazy problem. It's been like, well, the video is about 4 hours. It's been probably about 6 hours of my time. Um, I will go through quickly what this solution is doing. Although, keep it a buck, if you clicked on the 4 hour video wanting the best solution, I don't know what to say. But I did actually in this downtime look at the Reddit and implement some other solutions. But yeah, let's go through my solution first. Part one, it's pretty straightforward. You just do breadth first search. Part two, now we do something a little complicated. And so I don't know, I'm not gonna like explain something every little detail, but yeah, let's so looking at our scratch pad, we have let's just delete this all and redraw it. Cool. So we have our input that's sort of tiled. So this fucking annoying. Um, and say we have like a center tile that's like this. Essentially, we're going to build out an output that is approximately diamond shaped. Um, it's going to get like a little fuzzy on these edges, maybe, but approximately diamond shaped. And what I do is I scan starting at the center row. I look at this row and I use binary search starting with like a left here and a right here to find this tile that's partially filled in. Then I can compute how far this partially tile, like I can explicitly compute how many squares are filled on this partially filled tile. Um, and yeah, occasionally we'll have multiple partially filled tiles, but my code does handle that. Then I do the same thing, doing binary search on the left side. So from like there to there to find this boundary tile. Um, then I know that these three interior tiles are full. And full tiles, I have pre-computed the value. And so I know that there are three tiles here in this example. And so I can pre-compute like 3 times the value. Actually, it's a little bit more complicated than that because these interior tiles have two possible parities. So there's two possible values, but still we can we can handle that pretty simply. Then I go up to the next row, perform binary search again, find these partially filled rows, these filled tiles, explicitly compute the number of squares we can reach in them, and then since this one's fully filled in, we can compute that directly. Or we don't need to compute that, sorry, again, we can just use the saved value. Then finally up here, we have this partially filled square, no fully filled squares in this row. Then we check this row above. This square is empty, or this row is empty. So we stop our search going up. Then we do the same thing going down. For this row, find this, blah, 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 until we find our search. Now we've explicitly tallied up um, the number of hits in each one of the perimeter squares, and then we've computed using the saved value for all the interior squares. We sum all of that up and get our answer. And so with my optimizations, even though this is written in Python, I'm just slow. We computed it took only about 30 minutes. I say only. Obviously, there are ways to do this much, much, much faster. So yeah, I'll go through the code really
sort of quickly, but how this all works, I would probably just advise you to look through the code if you're curious. It's took me like 4 hours to program it. It's a little complicated. So in part two, the main function I'm using. So here I total up the the number of reachable tiles in. So I was talking about how we have parity here. So like the origin square and then squares that are offset by one. So if we redraw this as just like a 3 by 3, if this is our origin, the x squares have the same parity as the origin, and the O's and the blank squares have off by one, have like the different parity. So, and then this like checkerboard pattern continues. So we need to compute both these values for when we're doing this search and computing like the inner values. Or sorry, like totaling up the inner points. Then we do this, run this function called row loop, and what that does is it'll scan up. That's the first time we call it, and the second time it'll scan down. We can step into that. Okay, yeah, I'm not gonna go line by line, but big picture, we do the binary search to the right, then we do the binary search to the left, then we get our partially filled, we add up for the partially filled columns. Sorry, that's here. And then here is where we explicitly, or we add up for the internal squares that we already know the value of. Then we do that until we have 0 steps in a row, and in that case we break out. Yeah, and then to go into a little bit more detail about how we compute explicitly the number of squares in a partially filled tile that's really far away, is we can use the fact that, so this is our input. We have a start in the middle, and it's surrounded on all sides by sort of this blank, or this empty row and empty column. There's actually an empty row and empty column going through the middle too. And that means that when we're trying to get to a tile that's really far away, here, let's delete this. When we're trying to get to a tile that's really far away, so if think hundreds or thousands or even more, hundreds of thousands of tiles away, the most efficient path to get there is going to be going down these open lines. Since if we go through the middle, we're going to have to be like zigzagging all over the place. But if we take the open line, then we can just go straight to this tile. Or if it's say down here, we can go the most efficient route, since it's a Manhattan distance, like on a grid. Instead of going through the middle, having to zig around, we can just take this and then this along these like open corridors. And so essentially we exploit that fact to be able to count the number of squares available in each one of these faraway tiles. Yeah, you can look at the code, scroll back if you want to see exactly how I do that. But that's my solution. As far as I could tell, I didn't see anyone else that did it the same way. Probably because it's not a good way. But yeah, I'm glad I stuck it out and found the solution. Now, I did look at the Reddit and implemented a couple of other solutions. The first is sort of just based on visualizing. So let's, yeah. This is a visualization of the tiled input. So each one of these numbers is a tile, and then the number represents the number of squares, the reachable squares within that tile. Excuse me. And so this is with this small number of steps. If we increase that a little bit, you can see we have something like this. We increase again, we can see we have something like this. And what's key is that we can see that these numbers are actually repeating. Like here we have 945 on the edges. Here's 945 on the edges. We have 5623 there, 5623 there. The interior ones are repeating too. We have 7496 and 5770, the two parities. Those are all repeating. We can see that, yeah. So essentially we have a few different kinds of squares, but it's a consistent pattern. We could even compute by hand. Wouldn't be super hard. I'm not going to do it now. But from this, if we increase, um, if we just were to continue this pattern, yeah, the number 65 is relevant because that's what we get when we take the total steps modulo the input size, which is 131. That is equal to 65. Yeah, so that's one way to get to the answer, just sort of visually. A final way um, is by using fitting a quadratic expression. So I'm not 100% sure how this is all working. I would look at the Reddit, sort by the top comments for J21 solutions. But it seems like a lot of people did it this way. And essentially, what we do is um, find um, sorry, essentially what we do is fit a quadratic expression. So we see we're using NumPy polyfit. X's and Y's are defined here. X's is just 0, 1, 2, and then Y's is equal to the number of squares filled in with um, um, with a number of steps less than or equal to um, the scaled x, which is equal to x times 131, which is input size plus 65. So you can see there's some similarities between how the visualization works and how this quadratic thing works. So essentially, a quadratic, essentially this pattern is going to keep repeating if we have these key parameters where we're scaling by the input size and the offset, where the offset is defined by total steps mod input size. So that's the 65 thing. And so yeah, when we can get the coefficients for the polynomial, and then run it on the total steps scaled down. And yeah, that's the polynomial solution, which also works just fine. That's what we're printing out at the bottom, and we can see like this runs super quick. So yeah, that is that for this problem. I don't know. I feel like additive code, I mean, it's just like a problem that you solve using code. And like, it's not just using code, it's also using inspecting the input, doing some stuff by hand, maybe. I don't know. I don't really want to solve like competitive programming problems. I just want to get better at coding. So I think we're definitely past the part in the challenge where I'm maximally getting better at coding, but I'm still glad. I think I'll finish it off. I don't think I can do four more 4-hour problems, but hopefully they're easier. Fingers crossed. But yeah, I came up with a totally novel solution and it worked. So I think that's pretty cool, even though it wasn't necessarily the best. Um, yeah, so that's that. Thanks everyone for watching. I would honestly be shocked if anyone's made it to this point. If you did, leave a comment. I haven't got any comments, but that would, yeah, that'd make me feel good to know that someone was listening this long. And so yeah, thanks, and I'll see you on the 22nd, which is coming up really quick. In fact, it is the 22nd in Eastern Time. All right. Bye, everyone.